Okay, so capture. Just want to touch on very briefly about capture, just so you can understand how we do that. This is a conventional technique. This would be an amine system. So Fluor has this, or Mitsubishi Heavy Industries has a product like this. UOP, another company that has an offering like this. But it's basically what you do is you take a flue gas, you interact it with the amine solvent in a absorption column. That amine then becomes rich with the CO2, goes over to a stripper where you heat it, and so that's where the energy penalty comes in. You need to use steam typically to heat that solvent back up. It takes about 710 BTUs per pound of CO2 to get that CO2 off. Then it comes off as basically pure CO2, would go off then into a compression system, pipeline, off to your sequestration site. So this is conventional technology. It's out there. This is what we do for natural gas separations. Currently, at the scale we're talking about for like even a small coal power plant, never been done. It's just that we just don't have the scale going up to a few 100,000 tons of CO2 per year with a system like this. And the energy penalty is very severe. On a pulverized coal plant, for example, you're talking about maybe a 30% energy hit on that plant to run an amine-based system like this. But there is hope. There's some new technologies. I'm not going to go through a list of these, but this is just one I'm kind of illustrating here. These are some new materials that are solids that we can engineer at the molecular level to extract and grab onto CO2 that you see here stuck in the cavities of that material, and essentially ignore anything else in those flue gas streams. And being solids, now you can think about engineering these things into deposit them on surfaces, enhance their ability to move vapors and fluids in and out of a large desorption system that you would need with the solids. And just to give you an example of where it goes with something like this, this is a framework structure. It's a nice tubular material, so you can have the gases flow in and out over particles that might be a millimeter or so diameter. And what you see is that the CO2 uptake is up to about 25 weight% in a material like that. And if you compare that to an amine solvent, you're beating that by about a factor of 4. So you can load it up with a much higher capacity. But the real kicker is that when you look at the energy that's required to regenerate this material, that is, drive the CO2 off, you're looking at maybe 140, 150 BTUs per pound compared to 710 for that amine system that I was talking about. So there's lots of potential here with these new materials to get that cost and energy penalty down, something around maybe about 10%. And that's probably doable.